Good afternoon, everyone. So for those who don't know me already, I'm Paul Devost. I'm space mechanics engineer at Exotrail, and I will be conducting this second webinar on ExoOPS mission design. So we already performed a webinar 2 weeks ago, but for the people who could not attend this webinar, I will reintroduce a bit ExoOPS and the software we developed. So Exotrail is a new space startup, as most of you must know. And our mission is to bring agility to space. And to do that, we developed software, which is ExoOPS mission design and ExoOPS mission operations. It's a software suite composed of two softwares. And we also developed ExoMG electric propulsion systems, which are in fact the main product of Exotrail. And in this webinar, I will present a concrete use case using ExoOPS mission design, which is our mission design tool. So it will be a bit more advanced than last webinar from 2 weeks ago. The software would be free until the end of April. So you still have the possibility to test it. And if you want your trial version, you need to register. And just for the technical details of the presentation, I will be presenting for 35 minutes approximately. And now for those who couldn't attend the webinar from 2 weeks ago, I'll briefly reintroduce the software. So I'll try to be quick for those who already know everything. ExoOPS mission design is a user-friendly mission design tool, and it follows you from the conception to the operation of your mission. So I will show you how we do that during the use case. And what is important to note is that it has a particular focus on propulsion, and it helps you to understand how to make the best use of this propulsion system you are using with the software. And with such a tool, you can accelerate the typical decision cycle required by traditional software because it's really easy to use. So, as I showed last time, it's a cloud-based software. So here I have a profile, and I'm logged on my profile on a web browser. And quickly, the first things you want to know about the interface is this help menu here. So on this menu, you will find general guidelines, documentation, and video tutorials to help you navigate through the software and to help you understand how to make the best use of the various functionalities we offer. So if I click on that, you will see a bunch of videos in both English and French. And so, yeah, it's a very good way to begin with ExoOPS because it shows you pretty much everything you can do with the software. Very quickly, I will again go over the 4 modules that constitute ExoOPS. So we have 4 modules because we want to follow the user on every phase of the mission. And so that's why we have, first of all, a Constellation module that allows you to prototype your constellation and to compute many metrics such as coverage, revsit rates. You can study the ground station network. You also have a second module here, which is the deployment strategies module. And in this module, you can define the constellation you want to launch, and then you can define launch constraints, and the module will find an optimal deployment strategy. Then the other module we have is the analytical module, and it's very similar to the numerical module in the sense that both modules allow to compare the impact of different propulsion systems on the mission. And so the main difference you need to understand between those 2 modules is that in the analytical module, we don't perform any propagation, and we only compute results with function evaluations. And that makes computation very fast. So it allows you to perform parametric computations and to evaluate thousands of scenarios in a few seconds. You can perform quick trade-offs, basically, thanks to those parametric studies. And the second module is the numerical module here. And so this one, so it's pretty similar in the missions you can compute, but the difference is that we integrate the dynamics over time. And so you have more precise but slower simulations. And so it's not possible to perform parametric studies with this module. However, you can have a better understanding of the system and the interactions between, for instance, the power system, the thruster, and the platform on the mission. You can also, of course, as it integrates dynamics over time, you can take perturbations into account. So you can find the third body of potential, drag, SRP, etc. And so very quickly, the software is written in Java, and it's based in Orakit, which is a space mechanics library developed and maintained by CS Group. So we update the software regularly. We try to implement a new release every 3 months with new functionalities and improvements on already existing functionalities. So now I have reminded all of you what was ExoOPS mission design. I will present a use case using a version of the software that is currently under final testing, and that will be released at the end of the week. So you will be able to use all the functionalities I'm showing by the end of the week or by the beginning of next week. Okay, so to present you the use case, I will go over some missions that I already prepared. And the use case I want to study here is a constellation of Internet of Things satellites. So I will show you my constellation design. Here, so here I will try to go through the process of creating such a constellation. So first of all, I have my payload here that I defined. And if I click on the edit button here, I can see that I define my payload by the minimum elevation to define its field of view. And I chose it to be 10 degrees. So here, if you want to be reminded of what is the elevation, you can click on the tooltip right there, and you will see that it's the angle between the horizon and the direction of the spacecraft to the target. Then to simulate your constellation, you will have to define a mesh. So here I'm going to simulate my constellation over a world mesh. So if I want to create it, I just click on New Earth mesh, and then I can fill the longitudes I want to compute, and the latitudes also. So I have to provide a minimum, a maximum, and a number. So this will define a mesh grid, and for each point in the grid, I will compute statistics that I will show later. So here, I first built a constellation initial design, I've called it. So it's the design I want to test with my constellation simulation. And then I want to improve this design. And so my goal is to comply with two constraints. The first one is that 90% of the time, I want to have an average gap duration between two revisits of less than 15 minutes. And my second constraint is that I want an average age of information of less than 4 hours. So the age of information is the time elapsed between the point of interest and the next ground station field of view. So I will show that, but I just wanted to tell you the constraints I have for my constellation so you can understand the process of optimizing this constellation with the tool. So then when I go to the configuration of the simulation, I can choose my geometry. So here I've chosen the constellation initial design. Then for the Earth mesh, I'm selecting the world mesh. Then I will simulate on 10 days. I want to show those statistics. So I want to have revisit statistics, and I want also to compute some statistics on the ground segment. So here I've chosen the very dumb ground segment. So you will see that it's not efficient at all. So I've chosen a ground station in Kourou and a ground station in Toulouse. And we will see how to improve the performances of the ground segment later. And I think I forgot to detail the geometry a bit more, so I will go over it again. I've chosen 4 planes for my constellation. So I have some synchronous orbits at 600 kilometers. And I want to phase my 4 planes between 12 and 19 hours in mean local time at ascending node. So for the moment, I have chosen to put 4 spacecrafts per plane, but we will see that we will change this number later to improve the performances of the constellation. Yeah, and that's pretty much it. And of course, you need to compute the performances of your constellation, you need to select the payload you are using. So this is the payload we defined before with the 10 degrees minimum elevation in order to see a point on the Earth. And so when I compute a simulation of this constellation over the mesh grid that was defined, I have here a 3D map with a heat map overlaid onto it, and that describes the results I have here. And so I said I was interested in the gap duration, and here I want to plot the average gap duration in the 19% best cases. So I'm using this parameter here because when I go to configuration, I had chosen this ratio to be 90%, which means that I'm computing the results in the 19% best cases. So here I go back to my dashboard, and so what we see here is that this average gap duration can be at a maximum of more than 15 minutes here. So I have some zones near the equator where I have roughly 20 minutes of gap between 2 visits in average, and this being in the 90% best cases. And also, if I go to the age of information and I plot the same kind of statistics, what I can see is that I have more than the 4 hours I wanted in terms of age of information. So if I plot the map in 2 dimensions, I can see my 2 ground stations here in Toulouse and Kourou. And I can see that near those stations, I will have a very good age of information statistic. But when I'm far of them, I have this very big age of information of more than 5 hours, and nearly 6 hours, in fact. So here, what I want to do is to improve my constellation design, and I want to try something different. So what I did is I created an improved design for my constellation, and I went to the geometry panel, and I created a constellation so I can copy this design, for instance, and then I can modify it. And so here, if I edit this geometry that I used for the improved simulation, what you will find is I changed the number of spacecraft per plane, and I added 1 spacecraft per plane. So now I have 5. And also in the simulation, I changed the ground segment and I used other ground stations. So here I chose Kiruna and Perth. And when I simulate that, now I have an age of information in 90% of the cases that is less than 4 hours, as I wanted. So here you can see both ground stations. First one is here, and the other one is here in Kiruna. And then if I want to plot the gap duration and the average gap duration with the 90% ratio, then I can see that my worst average case is less than 15 minutes. So that's what I wanted. And now I'm pretty happy with my constellation design. So here, just so you know, you have other representations of the same heat map. So you can export them. You can do pretty much anything you want with them. And here, if you zoom on this one, you can have each point of the mesh grid, and you can obtain data such as the longitude, the latitude, or the coordinates on the planisphere, and also the statistics you want to look at. So yeah, that's pretty much it for the Constellation module. And so now we have this satisfying design for the Constellation. What we want to do is to deploy it. And so for this, we have a deployment module that I will show you right now. So here, I will show you the first strategy I studied. So the deployment strategy module is a module that allows you to understand what is the best way to deploy your constellation. And for this, you have to use launches. And so launches are defined by a launch date. You have to choose a launch orbit. And you also have to choose between a dedicated or a rideshare launch. And this will have consequences because a dedicated launch will be, most of the time will be more expensive, but it will put you just where you want to be put in orbit. Whereas the rideshare will be most of the time cheaper, but most of the time you will also need to maneuver from the orbit you are put on by the rideshare launch to your operational orbit. So we have created a bunch of launches here. So we have rideshares and dedicated launches. And for dedicated launches, you need to provide the maximum load and the cost of the launch. And for rideshare launches, you need to provide the local time at the ascending node of the launch because it is imposed most of the time by the rideshare. And you also have a maximum available load on which you can put a number of spacecrafts. And then to compute the cost with rideshare launches, what we use is a mass cost here. And so it is the cost you will pay the launcher basically to put a certain number of kilograms of payload onto it. Yeah, so what I did is I took the exact constellation geometry I defined previously in my constellation simulation. And here, for this first scenario, I chose only dedicated launches starting in January 2022 and ending in April 2022 for the last one. And yeah, so these are options that I will talk about maybe in the Q&As if we have time. But it's basically to optimize, to constrain the optimization of the deployment scenario. So you can have a maximum number of spacecraft per launch and a minimum. So here I put 100. So this way I'm sure I won't have any limitations on the finding of the best scenario because we only have 20 satellites to deploy. And then what is very important is to understand those two fields here. So it's the duration cost and the RAN maneuver optimization type. So basically the duration cost is a measure of how much a day of not operating your constellation will cost you. And so a simplistic way of thinking about it would be to think about it as the total value of the constellation divided by its life expectancy, for instance. So that's a rough way of thinking about it. And of course, things are a bit more complicated, but that's, if you want, you can fine tune this parameter to suit your needs and to reflect your particular situation. But yeah, the essential thing is to understand that every day spent into space, not operating your constellation or your spacecraft, will cost you money. And here in that case, we make the assumption that the constellation cannot generate any revenue until it is fully deployed. So that's important to know. And the other parameter here, it corresponds to a plane change maneuver that some satellites might need to perform once they are deployed, if they are not deployed on their operational orbit. And so if they need to change their plane, we provide a way of computing plane change maneuvers, and those maneuvers can be optimized either in terms of duration or in terms of propellant used. So this is equivalent to delta V, in fact. And so here we make the choice to optimize on the time. And then we have a delta V budget of 400 meters per second for this mission, which is a constraint to find the optimal duration for the mission. Then I will show you the result of the computation here. So here what we have is the result of all the configurations that are possible given the launches that I selected in the configuration. And so this is so here we only have one solution to deploy the Constellation. And what it tells us here is that I will be able to exploit my Constellation at this date, that the total cost of the deployment will be a bit more than 28 million euros, and that most of it is in fact the cost of buying the launches. Here I have a very small propulsion cost because I put a price of €1 per thruster, so it's 20 euros in total, but it's just to put something. And then the deployment duration cost, it's what I told you about the duration cost. It measures the cost of not operating a Constellation between the first launch and the fully operational date. And if I click on view here, I can have a detailed view of all the launch configurations. So here we only have one. And what we see is that we deployed the 20 spacecrafts on our 4 planes. And we also have a bunch of metrics here on the cost. So that's what was displayed on the dashboard previously. And you also find a list of all the launches and all the maneuvers that needed to be performed to change the plane. So here we don't have any run phasing maneuver here because there was one launch per plane. So we only have a small orbit raising maneuver because I think the launches are at 400 kilometers. So you will have a small orbit raising at the end between 400 and 600 kilometers. And so that's why you have a 15-day delay between the last launch and the fully operational date of the Constellation. So that was for the first strategy. And now, if we want to have a mixed strategy, for instance, we could make the choice to use different kind of launches. So here on this mission, I have chosen to use 2 dedicated launches and 2 rideshare launches. And the rest is identical to the previous deployment strategy simulation. So I will just jump straight to the results. And what we can see here is that the deployment will take a lot more time. So it will be also more costly in terms of duration cost. However, the launch cost is much less than in the previous case because with the hypothesis we made on the launch price, it's much more cost effective to book a rideshare than to buy a dedicated launch. But of course, you can change all those numbers and you can find the best strategy. It's not always the rideshare that is the best strategy, but here in that case, it's the best one. So if we click on detail view here, as I said, the best strategy is to use 2 rideshares. And then you will perform run phasing maneuvers. So we can see 4 of them here. And so the biggest plane change will be 36 degrees here. And yeah, then you will find the total cost of the mission, which is way smaller than the dedicated strategy. Here is the launch cost, so it corresponds to buying the rideshares. And then you will have a higher deployment duration cost because you have a pretty long maneuver to perform the 36 degrees plane change. And Yeah, and in the propulsion cost, so here it has a number that is much higher than the 20 euros from previously, because this time we count for the propellant that was put into the ride shares and that were needed to perform the plane changes. So the mass of this propellant is taken into account in the propulsion cost, because you need to put this mass of propellant into space to be able to achieve the maneuvers. And so if you scroll down a bit, you will find that the 12th configuration is the first one that is a mixed scenario with rideshare and dedicated launches. And so, yeah, the conclusion in that case is that the mixed strategy was not a very good idea, and that the best one is probably to stick with 2 rideshares. The other thing we can do here at this point is we can export the data we have. So you can select pretty much everything you want here, and you can export it as a CSV file. So what I did is I prepared an export already, so I can show it to you. So I will share my screen. So now you should be able to see my Excel sheet here. So here what I have is the export of basically all the raw data that was provided by ExoOPS. And here I've plotted the cost of each configuration of deployment. And also on the x-axis, I put the date of the end of the deployment, which means it's the date of the availability of the constellation. And so here, what you can see is that we have groups that are determined by the colors. So if you use 2 launches, the configurations that will be generated will be the 3 rideshares here. And then you can use 3 launches, and you will find this group. And then you can use 4 launches, and you will find this 3rd group here. And so what you can see is that for this case, for this particular constellation, it was much more cost-effective to use rideshares. So now I'm going back to ExoOPS. Nope. Give me a sec. Okay, so now you should see the ExoOPS mission design software again. And okay, so that's it for the deployment strategy. So now I've found my preferred strategy. So I will be using the rideshares. And now what I want to do is to determine what is the best propulsion system for my mission. And so I'm going to the analytical module because I will be able to perform parametric studies on the propulsion system to try to understand what is the best one for me here. And so here, if I go to the analytical module, I will show you a run phasing mission, which is basically the mission performed during the deployment of the constellation after the rideshare has put my spacecraft on its deployment orbit. Then it needs to rally its operational orbit, and so it has to perform a plane change. And so I want to be able to simulate that to understand what is the best propulsion system for me here. And so here what I did is I created a spacecraft with a parametric thruster. So if I edit my spacecraft, you will see that it's pretty simple to create a spacecraft in the analytical module. So you have to provide a platform mass, so it doesn't count the thruster. You can, if you want, define a drag model, but it's not mandatory. And then you need to provide the orbital average power for propulsion. So I explained that in the first webinar, and I will show you very quickly what it means. But the orbital average power for propulsion is the power you can use on average for your propulsion system on an orbit, and it will determine roughly the size of the thrust arcs you will be able to use on your orbit if the power you generate is lower than the power that is required by the thruster. So if you have any questions on that, I can answer them at the end of the presentation, or you can also look at the first webinar if you want more explanations. I won't go into too many details now because I need to be a bit faster than this. And then I compared, thanks to the multiple option here, two thrusters between one another for the same spacecraft. And so here, if I go on the thruster, what you see is that you can have a very simple definition of the thruster. So you need to put its thrust, specific impulse, and the nominal power, which is the power required to perform a burn with the thruster. And then you can input the mass, including the propellant. And then you have a bunch of options for the propellant mass. But yeah, I suggest you try by yourself. And then, so to perform my round phasing mission, I'm still going from my deployment orbit to my final orbit, which is the 600 kilometers unsynchronous orbit. And to do this, I will, same as before, optimize on the mission duration. I will still have the same delta V budget. And I will simulate a bunch of different run changes because as I can perform parametric studies in the analytical module, it's very easy to simulate a lot of different cases. So here I have 51 cases. So I'm going from plus 5 degrees to plus 45 degrees. And then we still have this duration cost field that represents the cost of not using the spacecraft for its mission during one day. And we also have a mass cost that we used in the rideshare, which is the cost of 1 kilogram sent into space by a rideshare. And then I think I showed it quickly in the first webinar, but what you can do is customize the outputs you will get from ExoOPS. So if you click on this checkbox, you will have a scripting interface that will appear. And so here you will find all the fields that you can use and that you can post-process with your own formulas. And so here what I did was I generated the ratio between the used propellant and the mission duration for my parametric studies. And so as you will see in a few minutes, I can use those scripting outputs in the plot interface. So this means that you can use all the post-processed data from ExoOPS to create your own results and to plot them if you think that some fields or some results are missing in our current implementation. And so here, if I go to the results, you will see that you can, oh, I will redimension that. Okay. So here I plotted the mission duration depending on the target delta run, which was parametric, and I can compare two different kinds of thrusters here. And what I can see is that for this particular mission, it's a bit more interesting to have more thrust than to have more efficiency, because my mission duration will be much lower if I have a bit more thrust. And here on this graph, so I'm going to change this label so it's easier to read. So this is the as you can see, it's pretty easy to edit in the plot interface. And so here, what I'm plotting is the cost of the mission, and I'm not counting the cost of launching the platform into space because it is the same regardless of the thruster used. And here in that case, what I can see is that because I had a big duration cost, then of course the best strategy will be to use the thruster with the more thrust because it will give me a smaller mission duration. But this depends totally on the parameters you put here. So if you have a very small duration cost because it's not important to you, and you have a very big mass cost because you are using, I don't know, maybe dedicated launches, then you will probably have different results. This is just to show you how you can make this kind of informed decision with the parametric studies offered by the analytical model. And then, of course, as I promised, you can plot the results from the script. So here I have my output, so it doesn't have a very nice name. So this was the propellant over mission duration. And let's say I want, grams per hour, it's fine. And then I will plot it against the targets that run at the mission. Oh yeah, and I forgot, of course, to add a parameter, and the parameter will be the spacecraft thruster name. And so here, so I don't know if this result is very useful, but it was to demonstrate what you can do with the scripting interface. So basically it shows you the ratio between the propellant used during this mission over the mission duration, and this is parameterized by the target delta run you want to perform, and also by the thrusters you want to use with your spacecraft. So if I take the 36-degree case, which was the most extreme case I need to perform with the deployment strategy I chose. So what I can see here, for instance, is that if I go to 36 degrees, I have 165 days to perform the mission with the ExoMP microthruster. And here, if I go to 36 degrees, I have 233 meters per second for the high ASP thruster. So that's it for this plane change. And then what you can also do with the analytical module, is you can even go a bit further than this and go to the sequence mission to the sequence mission, and so you will be able to simulate your spacecraft over its full life. And so here, for instance, I chose the same spacecraft with the two thrusters, and I also said it was going to be launched at 500 kilometers, that it would have to perform a run phasing until it reaches sun-synchronous 600 kilometers orbit, but I wanted to optimize on time, etc., etc. And then I want to perform a station keeping during 5 years at my final position. And at the very end of the life of my spacecraft, I want to deorbit it. So basically what the deorbiting does is that it makes the spacecraft maneuver to an orbit that ensures a less than 25 years re-entry. But if you wanted to estimate the cost of an active re-entry, what you could do is you could simulate a transfer to a 250 kilometers orbit, for instance. So that would give you a good estimation. And so for the station keeping here, I forgot to mention that you can customize the tolerance box on the semi-major axis, and that we perform both station keeping for the semi-major axis and for the inclination during the station keeping. And so here at the end, I have this dashboard of results again with all the important statistics of my mission. So that's pretty classic now. And here I chose to plot the plane change duration. So this is only the run phasing mission. And so here it's again, I can plot the duration depending on the target delta run and depending on the thruster I equipped the spacecraft with. And I can also plot the used mass for the mission. And so here it's the total used mass on all the phases of the spacecraft's life. So from the initial run phasing to the end of the orbiting. And so here I have a graph that shows me that I will use more propellant with the ExoMG micro thruster because it is less efficient than this high ISP thruster that was used to perform the same mission. So this gives you a way to make a trade-off between what you want. Can you embark a bit more propellant to be more efficient in terms of time, or are you limited in propellant and will you need to use this kind of high ISP thruster? And then if you go to the detailed view of this mission, you will have a detailed view of each mission of the sequence mission. So here we have the run phasing, station keeping, and then the deorbiting. And you will have a bunch of results, depending on what you are interested in. So yeah, here, for instance, what is interesting for system engineers, especially, is the number of burns that will be required for the mission. So you will know how many times you need to fire with your thruster to perform the mission, for instance. You can find maneuvering duration, delta V, of course, many results. Okay. So now I will go quickly. I think I will go very quickly to the numerical module. What I wanted to do was to perform a power system design of my spacecraft after studying what was the best propulsion system for me, and also to perform a numerical run phasing mission. Okay, I will go with the power system design, and then I will see if I have time for the run phasing. Because I want to let you some time to ask questions at the end. So here, basically what the power system optimization mission does is it takes your spacecraft. So here it's the same spacecraft as before. It takes the orbit on which it will be the moment you want to perform this simulation. And then it will simulate the spacecraft and tell you what is the power you can generate with your power system, depending on your attitude mode. So here what you can see is a plot of the charge of the battery and of the attitude mode, depending on the simulation duration. And so the numbers of the attitude mode correspond to the numbers you can find here. So for instance, the mode 1 will be the sun pointing mode. So if I'm in sun pointing, what I can see is that my battery is charging very well. If I'm in yaw steering, for instance, so number 2, it's a bit less, etc., etc. And so this mission will help you optimize your the settings of your power system and of your spacecraft. And so to understand a bit more what are the strategies available to use your power system, you can go to View. And in this detailed view, you will find thrust strategies and that will help you configure correctly your spacecraft. And so here, for instance, we have the orbit average power that we can have in sun pointing mode is 50 watts. So that's the number you will find here. And then you can change the duty cycle, which is the percentage of the orbit on which you will be firing. And it will tell you what will be the thrust duration, what will be the gap between the burns, and it will tell you what is the minimum charge for firing that your battery will need. So it tells you a lot of interesting information. So here, what you can see is that I have nearly half the power generated during sun pointing when I am velocity pointing. And most of the time, especially when I change my semi-major axis, I will be velocity pointing. So if I want to have a better power generation during velocity pointing, what I could do is go into my spacecraft. So it's this one, and I could change the solar panels I'm using. So here what you can see is I have deployable fixed solar panels. So when I'm not sun pointing, I will generate much less power than when I am sun pointing. So what I can do is use deployable rotating panels, and I can see what is the impact of this choice on my power generation. So if I do this, yep, I need to choose. I think I didn't save it. Yeah, I forgot to save it. So if I save this, and I save my spacecraft, and then if I go to my dashboard, you will see that a start recompute warning has appeared because the software detected I had changed one of the components of the mission. So if I recompute, yeah, so you will see I have a much better power generation, and especially when I'm velocity pointing, now I have nearly 50 watts. So I'm nearly at the maximum of what I could achieve when I was sun pointing. So yeah, that's basically what you can do with this kind of module. And you can also, what I was showing in the strategies, you can apply that to find the best thrust patterns for your mission. And so I don't think I will have time to show the run phasing mission. Maybe I will show it very quickly, but okay. So what I want to show you especially, so this is basically a simulation of the run phasing mission. So I already showed that on the first webinar. So if you want a bit more comments, I suggest you to watch the video, because I want to save time for the questions and answers. But yeah, what you can see here is we have added in this release maneuvering strategies. And to understand how to best parameterize those maneuver strategies, you can use the power optimization mission that I showed just previously. And so here, for instance, I can, so yeah, I will set my duty cycle to maybe 30%, which was what I had on my spacecraft. And then you can change the number, for instance, of rest orbits. If I put 2, oh yeah, my user now was locked. So here, what it tells me is I will thrust on one orbit, and then I will rest on 2 orbits, and then I will repeat this pattern again and again. And then you can shift arcs this way. So the power optimization mission will help you understand what is the best setting for your duty cycle and for your rest orbits, typically. Yeah, so for the results of the run phasing mission, so I will go over them very quickly. But what you can see is the first maneuver, the coasting phase, and the relative run change during the mission here. So yeah, with this last plot, I have finished my my detailed study. And so as you've seen, I went from my Constellation design improvement to how I would deploy this constellation, and to what was the best propulsion system for my particular case. And in the end, I could simulate it accurately to check that everything was fine. And so that is basically what you can do with this mission design tool.